All right. Thank you, Oriol, once again. All yours.
All right, excellent. Thanks a lot for the kind introduction, Ayush. I'm gonna give a fairly probably technical talk, but not going too deep into any particular area. I'm just gonna try to explain maybe through the lenses of my moving actually from, as you said, from Google Brain to DeepMind, how we experienced both reinforcement learning, because that's kind of what DeepMind, I guess, is most known of and about, and then also how I perceive kind of one tension I see now in the field, which is that of model-free and model-based. So I'm not gonna, there's quite a few great tutorials on both reinforcement learning and model-based, model-free RL, which I'm not gonna go too deep into, but at least hopefully you'll get some of the intuitions and perhaps examples so that you understand the tension between the two and how there's probably still a lot of work to be done in research. And obviously, I think this should be hopefully fairly informal. So please, during the talk, I'm very happy to answer questions. If we cannot, if you cannot go through all the contents, that's completely fine. So I don't know exactly on the online experience how to raise hands and whatnot, but I'm super happy to interact whilst the talk is going on. And of course, after the talk, I'm also very happy to stay for questions. Also, I must say that it's a bit of a pity that I get to come back to CMU virtually, because I actually spent a wonderful 9 months at CMU in 2006, actually, when I was finishing my undergrad thesis. So I actually have not come back to Pittsburgh or Pennsylvania, actually, but it seems like a very nice place to be, especially this week. And actually, one other thing I want to mention before beginning the talk is, we're going to talk a bit about world models and model-based, but the year is 2020. It's been a fairly difficult and out of distribution year for most of us, if not all. It's fine to have faced difficulties in several areas, and I myself, I have not been immune to this. So I just want to recognize that it's been a hard year. I think there's a lot of work to be done for the world to kind of get through the many challenges that we're facing. So hopefully things will be better. But at the same time, feel free to reach out to any of your colleagues or people that can support you when you face difficulties about isolation and things like this. I'm at home right now giving this talk. Is again not the kind of optimal setup to be coming back to Pittsburgh, Pennsylvania in a virtual status, but hopefully we can see each other soon. So yeah, with that note, I'm going to start with fairly basic sort of notation that might be useful, but this is just kind of to get us into the headspace of what I am most passionate about, which is about machine learning, end-to-end learning, and neural networks. So this talk, as I said, will be mostly focusing about model-free and model-based, and what, at least through my lens, what I understand as to be the challenges and current trends. But of course, it's useful to start from a very basic framework in which I think actually many things we see today in machine learning things fall onto, which is the following. I've been using this to explain a few things such as unsupervised learning, reinforcement learning, and so on. But in general, we have a source of data, which in supervised learning, which is probably what most of you are familiar with, comes through maybe a large collection of paired examples of images and labels, or sentences in English and sentences in Spanish that align with each other, etc., etc. Then there is a model that is trying to approximate the mapping that you observe on the training data from X to Y. Then we have a way in which this mapping, which has some trainable parameters, can be trained, that is to find the set of parameters through a loss and an optimization process so that the data is fit, and the loss function can be also very diverse. Increasingly so these days, we have interesting self-supervised loss functions, etc., etc. But I think a lot of what we see today in machine learning can be kind of seen through this lens of data. Where does it come from? What is the model? What's the loss? And what optimization process we follow? So since we're going to talk about reinforcement learning, let's kind of dive into what reinforcement learning is, from especially of the deep kind, which is where we have very powerful agent or function approximations. So actually, reinforcement learning can be seen pretty much the same way. In reinforcement learning, maybe one of the main properties is that, let me move this to maybe, yeah, to the bottom. Okay. So in reinforcement learning, we have an environment instead of a fixed data set. And this environment is the thing that generates data through us sending actions to it and it returning observations to us, right? So we can see actually the environment being the data source in reinforcement learning. However, a very interesting area of reinforcement learning is that of imitation learning, which will include, perhaps in exchange or in addition to the environment, a large data set, hopefully, of examples of agents that exist. That could be people playing video games, or it could be, you know, control systems controlling the heat in data centers and so on. And that could take the same format of, you know, observation or state to action. And this could be, in addition to the environment, quite helpful for some of the techniques that people are using nowadays. Now, the model, again, this is very similar. There's a mapping between the state and the action. That's what the agent is trying to do: observe the state and map it onto an action to optimize something, a reward generally. And then the loss function, you know, there's quite a lot of different loss functions in reinforcement learning, but perhaps the most traditional ones are Q-learning, in which you try to learn what is going to be the total return across a trajectory given the policy that you're running. And that usually is actually done through, you know, minimum squared error. And then there's also policy gradients, which actually looks even closer to supervised learning, because it's literally cross entropy loss of the actions you executed, but modulated by the amount of reward that those actions yielded eventually. You know, that's the advantage function that methods use, actor, critic, and so on. There is a whole great set of resources. I'm going to move this again. Okay. A whole set of resources that I recommend for reinforcement learning, and perhaps you know, David Silver has great set of video lectures, but there's really lots of nice tutorials that have been given in the last few years at the likes of ICML, NeurIPS, and so on. So reinforcement learning has gotten some attention in the last few years, thanks in part to many sort of different challenges that have been cracked through the lens of this very simple paradigm, and also by using a powerful neural network in the place of the policy, which traditional reinforcement learning typically use more like the traditional, if you will, pre-deep learning approaches that we saw, for instance, as well in computer vision, such as, you know, linear classifiers on top of features that you would handcraft. And there's really a wide variety of applications, lots of which are actually in video games, or in game domains, or in, you know, like kind of board games and so on. Today, I'll explain you a little bit through the lenses of AlphaGo and then AlphaStar, you know, that of model-based and model-free approaches. But there's really a lot of work that people are doing, have done, and will keep doing for many years, I suspect, with this set of techniques, or through the lens of reinforcement learning. So, going a bit deep into, like, from machine learning, reinforcement learning, into what, you know, how to explain maybe in one slide model-based RL. I like Chelsea's slide that she has in this bootcamp. That, again, if you want to get more into the details, I'd recommend you check her lectures. But, you know, in a nutshell, model-based involves an extra step, which is not only you want to optimize the total return, but you might want to learn something about the dynamics of this system, this environment that is giving data to you. And perhaps the simplest approach you could imagine is that you have the environment where you run your policy, it generates trajectories. And instead of just looking at how is this trajectory with respect to the expected return that I was expecting with my model, and then doing policy gradients or something similar, you're actually going to look at the trajectory, which has a sequence of states, and you're going to try to essentially estimate in some way by some definition of what this distribution will look like. These could be, Gaussian processes, neural networks, etc. But what you're going to try to do is, given the state and action pair, right? So there's a state that came from the environment, you took an action. You're going to try to model what is the distribution over the next state that you're going to encounter as the environment returns to you. And if you have such a model, you could then start thinking about optimizing without actually running into the environment. You could use your model, simulate the future, and then somehow get, maybe through gradient descent or through search methods or whatnot, try to enumerate all the possible actions that you will take in the future that would yield maybe a desired state, or a state that rewards you by a large margin compared to what you're currently getting, right? And so thanks to getting this model to be very accurate, and then doing some sort of optimization based on an action that you would use the model for optimizing besides your own policy that would just map the input to the output, you would hopefully have an improved action that you could use directly as the policy, or perhaps to improve your training signal. And these are different methodologies that different approaches have taken in the past. So what's critical then in model-based is that there is a model of the environment. Some people call this the world model, because it literally is about replacing your environment with a powerful model that would be used instead of the environment. This model could be differentiable, could have very nice properties. Obviously, the control is a very big field that relies a lot on generating these sort of learned dynamics and then optimizing for certain conditions to be met. And it's a very powerful paradigm that I will contrast now a bit into kind of pros and cons, perhaps, between model-based and model-free. So model-free is actually maybe the pro that I see as the main pro is that it's simple. Model-free, you just get a state. You have some model that is a complicated nonlinear function of the state and maybe the past states that you've observed, right? It could be still a model that has memory. And then it just maps it to an action, right? So there's nothing to be predicted about future state, or you don't predict future reward. Maybe you predict the future return because that enables better gradients and better losses. But overall, the policy, once you deploy it, is simply input to output, very similar to all that we do in supervised learning. And that is a pro with its simplicity, but it also feels like a con because, well, a policy that takes constant amount of time to compute the optimal action, no matter what the situation is in, feels also kind of imperfect, right? Like, I mean, who has played games, especially those that require deep thinking and planning, which is a word that usually you use in exchange of search or model-based. Well, sometimes it's trivial what to do next. Sometimes you require really a lot of deep thinking. And it just feels bad that you would have a constant time policy, no matter the state you're encountering. At the same time, we are in the era of very deep and powerful models. And so you could kind of see in a way that the depth of these neural networks, like networks that might have 100, 200,000 layers of computation, maybe perhaps these layers of computation are, when needed, being used implicitly to kind of make a plan, or maybe just really dissect the state space in a way that search methods do explicitly, but doing more so implicitly, right? So maybe that's okay. And in fact, this is a current hypothesis that I actually believe might be true, that given a sufficiently deep model, as long as you can train it, that is a different question about regularization, trainability, etc. It might be actually possible to simply go without search and have these purely constant time / reactive kind of policies. And in fact, with this approach, which is very simple, lots of different demos and systems have done quite incredible things, such as initially DQN was such a policy, like that was how deep reinforcement learning was first introduced to many of us through the paper from DeepMind in 2014. Then AlphaStar, which I'll describe a bit later. Robotics in part can and is using model-free in some applications. Other game domains such as DOTA 2 capture the flag. And I will say maybe it's not reinforcement learning, but it's worth saying that all that we're seeing in language modeling and machine translation currently is of this kind of no planning about how should I complete this sentence or answer this question with a deep neural network without planning. Most of it is purely reactive, generate the next word, and given the next word, generate the next word, and so on. Now, that being said, there's something fundamentally that feels right about model-based. And if you read Chelsea's sort of lecture, you will see that the main reason why model-based is interesting to many of us is because it achieves a few things that we feel current models are lacking. Sample efficiency maybe being the most notable one. Most of model-free models require years and years of experience through training to be good at a game that they just start playing. And even if the game is simple, that's usually is the case. Whereas for model-based, it is believed that you might train a model once and maybe reuse the model to gain in data efficiency when you train on a slightly different version of the same domain, for instance. Similarly to that argument, that of transfer learning is quite believable. We are faced every day with new challenges about motor control with our own bodies, and we generally don't fall even if we face a new set of stairs and so on and so forth, because we can sort of predict what each movement is going to imply. So model-based feels very natural, and it feels something that possibly we are using every day to solve problems about control, but also about playing games, creating things like text and so on and so forth. So there's a good reason for obviously thinking model-based is a worth avenue to keep improving. And in fact, as I said, what all that it changes is that in model-based you want to probably explicitly, but there are some models that do more so implicitly predict future states that you have not observed that with the idea that you build a world model that you then use to simulate and optimize the policy, right? So if you know kind of how each action will consequently change the state, you could plan ahead and really perhaps be better at many of these properties that are desirable and what people expect model-based to shine. And also there's a very nice essay that is called The Bitter Lesson from Rich Sutton, which wrote one of the most widely used books in reinforcement learning. And in The Bitter Lesson, basically one thing that Rich concludes is that the two methods that seem to scale arbitrarily, he says, is that of search and learning. It's hard to disagree with the fact that learning scales, and even today we're seeing models that are scaled up even more and perform even better. So it's very hard to argue against that. Learning is scaling very well. That's why we're seeing what we're seeing through the years with just the pure scale of GPUs and other hardware. For search, I think I'm not so convinced yet, but obviously these kind of statements came at the time where very major results, such as the ones that we saw playing the game of Go, notably, and also other things like that we saw other breakthroughs, poker included, which I think CMU had a great part on as well, a great project on these. In part, use this idea of search, right? So clearly, search also has enabled some interesting breakthroughs, especially in control, which I haven't even listed. And I'm going to describe maybe as a first example, because that's probably the one that's less obvious to people, the story between sort of AlphaGo and AlphaZero that used the idea of search to create perhaps one of the most widely known stories in the last decade in terms of AI successes and benchmarks. So I hope this is clear. We're going to dive a bit into details about how to train, especially model-based, and how to expand maybe capabilities of model-based. Towards the end of the talk, I'll describe some new research that we've been working on. But it would be a good time if you have any question now to, I don't know, talk, or I don't know how to do that, as I said, but I would be very happy while I sip some of my tea. It's tea time in London. Great.
Okay. If you have a question, you can unmute. There's one question. Yeah, you can.
Yeah, okay.
Hello,
yeah.
I'm personally a big fan of AlphaStar. Like
nice,
I watched the games at BlizzCon. So like for AlphaStar, like there are many behaviors that we cannot understand by AlphaStar. For example, when it plays terrain, the walling, you mean how you place buildings on when you play, is not efficient by AlphaStar. I think is that because this model-free assumption, and why does DeepMind decide to use model-free assumptions for AlphaStar? So my guess is that because when you transfer from your predecessor AlphaGo to AlphaStar, because StarCraft is really a complicated game. You don't have your opponent's information. Is that why you change to a model-free approach?
That's this question precisely. I'm going to answer and build up to the answer so that I can give it perhaps better in terms of the flow of the talk. It's a great question though, and you know, as I was alluding to in the very first slide, this is more of my almost personal process through learning these techniques through experience. So the fact to explain first AlphaGo actually, which is a model-based approach, is precisely because temporarily that's how I got exposed to sort of games and reinforcement learning. But precisely we didn't use model-based not because we didn't want to, but because there are fundamental limitations that I'll get to in a second. But that's a great question. Thanks for asking that. Great. Any other questions that I'll answer, I guess, hopefully through the next 10 or 15 minutes.
Yeah, I actually had a question on the planning aspect. You mentioned that the model-free might end up planning if they're very deep, and I found that to be extraordinarily interesting. Has there been much evidence in this regard? Because it seems as though as you scale the depth or the number of parameters to infinity, we're sort of saying that this computation we can trade in terms of time. We can take the amount of computation we can do, and we can hypothesize any type of structures that can be created in some sense.
Yeah. So this is a good question. I think what I mentioned, let me back it up maybe with perhaps a set of research that is going on a actually field that maybe you're not expecting the answer to be part of. But I think there you might find very interesting answers that might hint at what I said in terms of very kind of, I think intuitively, this is what might happen, right? So currently there are, as I mentioned this actually, there's the language models. Everyone is starting to be exposed at very cool demos about, you know, models that predict the next action, which is a word, given all the previous actions and so on. And these models don't have a planning component. They don't try to write kind of what the answer will be, and then given what they wrote, sort of go back and rewrite a part of the answer. They are purely sort of reactive in that they just spit out a word, and given that word, they spit out the next word and so on. But there's a lot of good work and papers that analyze both the architecture, which as you might have heard, and in fact in AlphaStar we use this architecture as well, called transformer. So there's a lot of very interesting work done mostly in NLP or natural language processing conferences that try to understand what the transformer, which is a very deep kind of graph neural network way of thinking about its inputs, you can almost see how it's building up sort of reading from all the past words that it observed. That's all it has access to, but iteratively possibly building up sort of knowledge from the past and probably storing it into some sort of working memory as you go deeper into transformer and heads that transformer uses, and eventually decide on what comes next in terms of word. But that's what I say, like intuitively, it feels like this very deep and very complicated kind of high order thinking of models that look at the past and try to predict the next time step optimally are doing actually some sort of implicit planning. So maybe that's a field to look into more into for evidence and interesting work. I'm not aware of like a particular paper, but I know there are many that try to understand how transformers are building up knowledge to answer questions or do all sorts of very interesting analyses. So hopefully that is an like a good enough answer, because obviously I gave a very kind of vague intuition, but since you asked, I mean, that's how I base my intuition on by looking at these kind of papers and analyses others are doing in language.
That's very interesting. Thank you.
Yeah, great. Okay, let's move on. I like the questions, so maybe I'll pause in another time for more questions, perhaps when we transition from AlphaGo and AlphaZero to AlphaStar. But let me just kind of give you a recap of a few models. Again, in model-based, there are quite a lot of different models that combine and mix and match these components in very creative ways. But overall, I think it's useful maybe to characterize and visualize sort of the styles of model-based and model-free we will see. Model-free is fairly simple because model-free just has feed-forward inference. It doesn't use a model, and then the loss, of course, you can use Q, policy gradients, and they are generally applicable. They can be applied to any environment. There's kind of other models such as model predictive control that is kind of very basic kind of model-based idea of predicting the optimal action by backpropagating through this state transition function onto the action to find what the optimal action would be. That works quite well for robotics. Actually, this was one of the early applications that was quite impressive. And then perhaps actually I just listed because it's quite a very different way to use a model. There's a paper very interesting by David Hahn, Schmidt-Huber called World Models. And it actually uses the policy itself is feed-forward. This is just the standard like state to action policy, but it actually learns a model of transitions so that it would use this model to generate extra training data, right? So it's a bit of like, it's more in the loss side of things you use a model because you have your feed-forward policy, but then you train a very good model of the world. And then instead of using the real environment, you just simply query your world model to generate or based on data coming from this model. And then the policy you end up training happens to work well when you deploy it into the real environment, right? So this is a very interesting, different maybe angle to model-based that it's worth discussing just briefly, because that's one kind of, you can see how you can mix and match all these things, but it's hard to make a complete list, but at least these two I thought worth mentioning as a kind of prior and setup for model-based. So let's talk about AlphaGo, and this is where the story gets also a bit personal, because I happened to move from California actually to London in early 2016. At the time where AlphaGo actually was being released, and 2 months after joining DeepMind, I go to the office at 4 a.m. to witness sort of the games that AlphaGo was playing against Lis et al. So it was a very exciting moment to be joining sort of the reinforcement learning, deep reinforcement learning, and sort of this idea that we can train neural networks end to end to play very complicated games, right? So it was a very special moment. And it was very nice to be able to leave it from within the offices that created these algorithms. So as you might know, Go was regarded as opposed to chess as sort of a domain that would take perhaps another decade or so to solve. But I think the clever usage of neural networks really enabled the breakthrough. So and these neural networks actually were used very heavily in a model-based setting, although it evolved a bit during the project, right? So, chess, as we know, it's reasonably complex. I think branching factor might be on the order of 17 or so, but don't quote me on that. But Go has like a much longer horizon. Games last definitely more than 100 moves. And also the branching factor in Go is quite much higher. And also, as with chess, it's one of these kind of domains that people thought, machines will never be able to beat us, or it will take a long time, and raw compute power, right? So even though raw compute power in theory can play very well games such as chess and Go, what was utilized in AlphaGo, the very first version, where was the idea of learning and search at scale, which really resonates well, because that's precisely what the bitter lesson sort of talks about. And it really is actually a quite simple approach. It's quite elegant, I would say. It's very impressive. I was really kind of impressed to see the usage of neural networks, which at the time I was only using for like, oh yeah, sequence to sequence and sequence and supervised learning and so on. So the main idea in a nutshell is to train a policy network that we know what it is already. It goes from state to action, and it's obviously a distribution over actions. It's not a single action that comes next in complex games that have large branching factors. So you train this policy, perhaps using professional moves that you have a data set of. That's how the first version was trained, actually. And then you train a value function that's probably the hardest part of Go, to identify who is ahead, as opposed to chess, where the pieces have certain values, and as a heuristic, those work reasonably well many times. In Go, it's very hard to identify who is winning in these kind of complex patterns that you see in the board. I myself, I'm not an expert of Go, so forgive me, don't ask me any questions about the game, but I'm happy to answer StarCraft questions on the other hand. So the value network, the function is what it's trying to do is just predicting who is winning. Again, supervised learning, binary classification, or three-way if you consider draws, which actually happen in these games. And again, super simple, right? These are the two ingredients that are trained in AlphaGo, trained in a sort of feed-forward fashion. In fact, they're not even recurrent. There's a single state of the board. You see the whole board all the time. And then you predict these two things. Where am I going to play? Who is ahead? And the model, so you train these, as I said, supervised learning, and then you run your policy, and then you start sort of training this value network of who is winning games, which is very important to understand the dynamics of the game of Go, given what you're currently at in terms of level of play. And really the search part comes in AlphaGo, the first version, mostly in inference, right? So you have these two components, and what you do with both of them is kind of almost like the obvious thing you would think in retrospect. Everything sort of seems obvious, but instead of doing brute force exhaustive search of all the possible Go movements, which, you know, it's a turn-based game, it's fully observed, so you can actually exhaustively search for the optimal moves if you had a lot of compute. What you're going to do instead is reducing the branching or the breadth of the search through only expanding those areas that look likely to be played under the current policy network. And at the same time, instead of rolling this search all the way to a terminal position where you can declare a winner in Go, you're going to truncate the search and at some point trust your value network that is a function approximation of who is actually winning. And then you sort of reduce drastically the amount of simulations or expansions that you must do at the expense, of course, of making them more computational, right? Exhaustive search is very cheap. You just place a stone, which is really like constant in time. And then you run your Go board program, and then you do it over and over and over. It's very sequential. It's very cheap in theory. And what you're doing instead is using very powerful neural networks at each node, perhaps twice if you're in a terminal state, to compute the value as well. And this enables you to reduce the sequentiality of the search, of the exhaustive search that it would be required at the expense of using GPUs or TPUs or what have you to sort of reduce sort of what the whole subtree would look like, ideally into a single very dense computation that involves a ConvNet in the game of Go in particular. That again, maybe going back to that intuition and great question, these might be sort of replacing the proper planning step, distilling that process into a single network that is trying to implicitly do the planning that would be required to expand, for instance, this node all the way to the end of the game. So AlphaGo, it's really that. It's mostly at runtime you run this search, but the training is actually fairly straightforward. It's not, the model is mostly used, let's say, during inference, right? So when you play against the professional, you run this search, and the more you search, the better it gets. That's the bitter lesson. AlphaGo Zero went just one step forward, which is it used the improved policy that the search gives to you to actually distill that, and it literally used knowledge distillation. So it distills the search capabilities onto the policy network itself, right? The way it did that is actually fairly intuitive again. You start with, let's say, a random policy and value network. You run your MCTS, that's the set of heuristics that are used to which nodes you expand and so on. I'm not going to explain too much what MCTS is, but again, great tutorials do exist elsewhere. So you have this process that, given policy and value, generates a move. This move happens to be better than the policy would give you if you just sample from the policy. That's critical for this process to work. And then you take this move, then you move, then you compute what the next move should be for white, and then you do that over and over and over, right? And so at the end, you obtain a trajectory or a full game of Go. And then what you're going to do is you're going to do two things. You're going to say, well, the moves that I created thanks to the search algorithm were improved from the base policy, right? And that's, instead of doing gradient descent, which you couldn't possibly do, that's the model-based part. You do search to use the model to find a better action to take, right? And once you have the better action as a target, you use that in a distillation fashion to say, hey, after using the policy in the value network, I think a better distribution over moves for this particular board position would be, and then you give that as a target to your policy network, which you're about to update, okay? So you retrain your policy network on all these improved moves thanks to the policy value and MCTS search. So that's the model-based part number one. And at the same time, you've played this game to completion, one side or the other, won or drew, and then these particular result you will use to regress and to train a better, ever improving value function that is also sort of distilling all the knowledge that is induced by the policy and value itself onto a new value function that improves the policy further, right? So this is kind of a self-improving loop, and this actually is all happening during self-play, right? So it's a very cool and elegant closed system that from nothing, it creates a very strong performing Go bot. And indeed, as you might have already seen, even though the first AlphaGo was quite strong, and that's the one that you saw winning against Liz et al., AlphaGo Zero, starting from scratch instead of from the supervised learning data that helped to train the policy, eventually surpassed, you know, the ELO score or ELO rating of the base policy. So that's just the progression. As I said, data efficiency, even in this case, it's model-based, but because it starts from scratch, is perhaps not the fastest. And then in our set of algorithms, we can add this now that I would say this is more about AlphaZero than AlphaGo. AlphaGo had MCTS at inference time, but AlphaZero added additionally to this process of distilling in the loss, distilling from the search to keep improving the policy, which created this vicious cycle of improvement, and indeed a very good result. There are a couple of issues from this algorithm, precisely as I was saying as well, which prevented us from just trivially applying these to other domains, which I'll go a bit into detail as we move from Go to these non-deterministic environments. Go is a deterministic environment. In AlphaGo and AlphaZero, the ground truth transition function was used. So actually you were not using a model to model transitions, but you were actually using sort of the ground truth to predict future moves a bit better and create this improvement loop. But again, maybe it's also a good time to sort of pause before sort of now, you know, enter my own sort of willingness to do research in reinforcement learning and sort of facing some very real challenges from spanning from these algorithms that even today, I think there's still like quite a few open problems to be able to apply these very powerful idea more generally, but lots of progress as well as I would say. So again, if there's a question, feel free to ask in the next, let's say, 15 seconds while I, again, drink a bit more of my tea. All right, great. Hope that's clear. AlphaGo really was a very sort of one of the most creative pieces of research end-to-end that I've seen, even in, I would say, my whole career doing machine learning. So really impressive, but again, some limitations that I'm gonna start kind of diving into. So we are in 2016. We kind of really did quite well in the game of Go. Game of Go as opposed to chess, and obviously Atari has some very nice properties that it's multiplayer. So it's hard to be the best because you can always play against yourself and essentially draw instead of win. And in action space was kind of a step up from definitely from chess and Atari. But you know, it had a few characteristics that still made it reasonably close to perhaps chess, other than a bit, an order of magnitude more branching and maybe in terms of moves per game depth. But at the time that this happened, Blizzard sort of almost, I think it was actually a tweet, believe it or not, was sent by Blizzard, the company that makes this real-time strategy game. And they said, okay, you've done well at the game of Go. How about this real-time strategy game called StarCraft, right? And as it turned out, we actually visited their headquarters and we started a multi-year project to kind of first create an environment and a data set for people to play with these sort of challenging domain, real-time strategy domain for the community. And then we started really seriously trying to build an agent that plays the game at the highest level as you could imagine. And that was nice because StarCraft actually had been used for quite a few years by the AI community already as a test bed. So it felt also natural as a kind of, okay, what's the next thing that comes after these sort of games? And it felt quite nice to be working on that. But it's quite difficult to apply, especially exactly what AlphaGo does in a game like StarCraft. And I'll try to give you sort of a almost run through to what the game is about a bit if you don't know that, as well as highlighting why model-based feels such a great idea. And it actually still is a great idea how people play and face the challenges in this game, but how it's actually quite hard to apply the techniques that we knew at the time in 2016, basically. So StarCraft it looks like a board game. If you zoom out like this, this is a very zoomed out version of the game. You're over here, you're gathering some resources, you're building new buildings, you're building units. So it's like a chess that you decide what units to invest in, exchanging them for money, which is in the form of these crystals that you can gather and gas. And very obviously, as you see this game unfold, you see that you're not observing the full state of the map all the time, right? Sometimes you go into this, which is the opponent's base, and you see what's going on there. But many times you're in the blind, right? It's a partial observable environment, essentially. But model-based makes a lot of sense, right? StarCraft has two main components, roughly speaking. One that is macro management. Macro management is that of just strategically, what should I be doing right now? Should I be investing in my economy? Should I be building these kinds of units? Should I be attacking you? Should I be defending? Should I be doing all sorts of like macro-based decision? And because of partial observability, you as a player must plan what's the optimal reaction to what's happening without obviously seeing what's happening all the time, right? So you need to replan what units or what to do based on evidence that you might be gathering because you're either being attacked or maybe you're going and you decide to sacrifice a bit of economy to scout what's going on. And all these decisions need to be happening obviously at real time. This is there's no turn-based. This game is like sort of real time as it gets. But planning at the macro level is very important, right? So that's number one. And number two, when there's a little fight, right? So when these are like blue versus red, right? When you're fighting and engaging with the opponent, there's the aspect of micromanagement, which it's a bit of like simulating in this now little combat or skirmish. What should you do? Should you attack this unit? Should you retreat with this unit? Should you load your unit into a transporter? Like there's all sorts of different decisions that you must do very quickly. By the way, this is fast paced, right? But these decisions, if you could model, and in fact, many of the current bots that play StarCraft actually have a model for how these combats will evolve to then plan to see whether they should engage or disengage or run away or and so on, right? So for both main components of the game, model-based feels like a really excellent idea. But there's quite a few buts that basically made it almost impossible to even conceivably start working from a kind of spanning from AlphaZero approach on this game, especially in the very early days. First of all, for now, we still require the simulator of the game of Go, which is very cheap. It plays a stone and the stone appears on the board. But if we are to use the actual game to simulate rollouts, the game is actually expensive. It's a modern game and it cannot be run very, very fast. So you cannot possibly use it at runtime. And on top of that, how are you even gonna use the game where you actually don't know what's going on the opponent's base, right? So partial observability and dealing with uncertainty makes it very hard for you to be able to plan when part of your plan is sort of relies on something that your opponent is doing that you're not seeing, right? So it really is hard to kind of generalize AlphaGo or AlphaZero to these kind of partial observable environments, which StarCraft is a very notable example. Also, actions in this game can have very different time effects in terms of immediately seeing, in Go or chess, you do an action and then something happens, right? The board changes thanks to your action. In this game, there are some actions that actually are completely no ops and irrelevant. There are some actions that are very tricky to deal with, such as moving the camera view of the agent. That's an action that it's very hard to sort of get the value out of when you do it, and you don't want to do lots of them, but you have to move the camera to play the game. So these actions can have very long-term consequences, like building an expansion. Only later on you'll start getting economical advantages and so on. And to name another one, the action space, which is really fascinating in this game, is much larger than Go. This is not like hundreds of actions. It really goes to kind of combinatorial sets of actions, which I can explain in a second. So more details, I'm going to skip sort of the details of the whole project, and I'm just going to focus on the model-free bit, which is what the architecture is doing. And to understand what the architecture is doing, we need to understand quite well the actions of this game. And this is a game where you basically select a group of units, and then you say, hey, to this group of units, I want to do this crystal-looking dome in this location, right, in this ramp. And this is a single action that you must do, and you do these actions. As a human, you might be doing about, if you're quite good, 400 actions per minute, and games might last, tens of minutes, right? So there's quite a few of these actions, and these actions, strictly speaking, are combinatorial, because you must decide which subset of your units are you going to issue what action, and then where is this action going to be executed, and so on and so forth. So it's quite a difficult sort of action space to dissect, and probably even harder to search over, because the branching can be as large as all the proper subsets out of the 50 or 100 units that you might own at any time to see which ones are you going to pick as a subset, for instance. And as a result, we designed a fairly standard, with standard components, architecture to deal with, to map literally in a model-free basis from the inputs, which are like sort of all sorts of observations you see, such as the minimap, and then what are your units and so on, through very standard components in deep learning, like LSTMs, transformer, ResNets, and pointer networks, basically. And this was a feed-forward network that integrated over time what happened in the past. So there's a memory component that's very crucial, thanks or in part due to partial observability. And then at the top, we sort of generate this action as if it was, a sequence of little instructions, right? What do you want to do? When do you want to do it? Who is going to do this thing? And then where, last and not least, where are you going to issue this action on the enemy unit, on your own unit, on this location in the map, and so on and so forth. But amazingly, these alone, without any planning, even though we really thought we must use planning, or we must use hierarchical reinforcement learning, which is another big field that so far hasn't panned out maybe in the biggest or the largest of environments that we've tackled, these alone was able to play the game quite well. There's another reason why that I will just skim over, which is to train these with reinforcement learning is actually quite hard, because the number of actions is astoundingly large. So it was asked in the question, like, oh, sometimes your agent makes a mistake and it might make a wall of buildings, but the wall is not perfect. And it's maybe not surprise for the agent not to be as precise as maybe the best professionals in the game, because at the end of the day, a main component to train these was going kind of almost backwards from AlphaZero to AlphaGo and utilizing expert demonstrations to bootstrap the policy, right? To make the policy sort of play the game in a reasonable way. So without going again into a lot of detail, we have a very big data set of games of StarCraft that many people like yourself, if you play, are going to be recorded by Blizzard anonymously. these games are shared with the whole of all of the community. And then the very basic principle of model free was applied without even reinforcement learning, right? So the first step of AlphaStar is literally copy the action that the human did, given all this sequence of observations up to this point in the game. And that loss to predict kind of the word, if you will, of the action, that the action is composed of several characters, if you will, and you want to generate the word that is the action you're going to send to the engine. That set of techniques is literally equal to what you're seeing today with language models, translation models, and so on, right? Is literally the same kind of model, the same kind of laws, but for a very different purpose, which is to create a policy to then play the game. And there are more steps to create the agent. These going from no data to this imitation learning data was very big boost, but there's more things. And for that, for all the details about the AlphaStar project, you can do one or two things. One is obviously go and check out the paper that we published actually a year ago, more or less now. So it's been quite a while, about how we combine imitation with reinforcement learning, how we ensure diversity of strategies. That's a big theme in StarCraft, etc. And if you're more into StarCraft and you want to have some fun looking at actual games, you might actually look at some of the events. We had sort of a I hear some noise. I don't know if someone is unmuted, but it's okay. But if you wanna sort of see the games and kind of see the live stream that we did, there's some materials available on YouTube of also many people that were enthusiastic about the projects from the gaming community, which actually was the highlight for me, to see all the energy behind the game and all the professionals and casters like kind of explaining how AlphaStar might or might not be playing. So take a look at these things if you're into the game. And I just want to finish the talk with kind of research that's actually not, part of it is published recently, which is MuZero, which I think in part will solve a big issue that we faced when we thought about using model-based in StarCraft. And then the other is more, even more exploratory, that we haven't even yet published, but I think intuitively, hopefully it will make sense. So going back to model-based, okay, there are quite a few limitations. That's why we couldn't really just use model-based directly into a complex game like StarCraft. I mentioned this, so I'm just kind of gonna say the obvious. Like if your environment is a stochastic, then you need to plan with this stochasticity in mind, right? You need to account for what the environment could play, so to speak, so that you can act or plan optimally. There's obviously, you cannot always think that the actions of the opponent, right? In Go or in chess, it's very natural to know, oh yeah, the opponent is like myself. It's very symmetric. But if you're playing like RoboCup and maybe the robots from the other team are a different model than you cannot know what the action space of that team of robots is going to be, so that you can plan or what all the kind of combinations that could happen, right? So planning in action space is quite difficult. And last but not least, as I was using StarCraft, but there are other even simpler domains like Stratego or poker that you see this partial observability is a challenge of even the current AlphaZero and even MuZero that at least leaves one of the properties or necessities from the AlphaZero algorithm. And last but not least, this one is a bit trickier even today. I don't think this is far from solved. But when we plan, we don't want to plan every single action, right? I don't want to be planning when I play a game like StarCraft. Where am I going to click, the next millisecond, and after 50 milliseconds, and after 100 milliseconds? You don't plan like that, right? You plan in a kind of abstract level, right? You're planning, oh, I would like to see if there's a base over there in that location of the map, and then you're going to plan accordingly how to execute that, how to gather that information in the micro or in the action by action level. So temporal abstraction is a very big deal that I think in reinforcement learning and model-based planning, it's quite open, and it's that we don't plan at sort of muscle by muscle and signal by signal level at when we control, let's say, our own bodies, right? So this also is a very big problem for all the methods. So let me describe couple of key ideas, and I'll leave the talk with that perhaps, because we're a bit over time. So the main idea of all this, I think, new work that's coming up in model-based is that you don't want to plan over the states, or you don't want to plan over actions. You need to plan over a compressed version or a simplified version of these states that you're dealing with, right? Your model needs to be ideally operating at a level of abstraction that's not as detailed as every pixel, but that it also does not require you to plan every single time you need to take an action to do something. That's just too much. So one thing we're proposing in this work that, as I said, will be published soon, is to use really very basic ideas about vector quantization that we actually published in 2017, to essentially, as a first step, we take all these trajectories of states and we compress them onto a single integer that is a vector quantized version of an autoencoder, right? The details, again, they're important, but the main idea here is that we want to observe how the environment is changing from when we send an action to the environment and when the environment sends us the next state. And that transition, we want to model it, but we want to compress that transition onto an integer for the reasons that are going to be obvious, because we like discrete spaces to search over, right? But this is an important detail, right? Like, we want to model transitions of state and action to what is the next state going to be like with an autoencoder. Like, just basically that's the model base directly mapped to this particular architecture, but with a discrete representation. And I'm just going to maybe compare at more like concrete level how all these models operate, right? So in AlphaZero, you need the simulator, and then you send an action to the simulator, move a piece in the chessboard, and then you have the opponent action, which you need to know what the action space of the opponent is. And you say, well, the opponent is going to move and issue this instruction. And you unroll this for a few steps. And that's exactly how you're sort of creating your value for this particular move is going to be represented by sort of a min-max game of what you end up with when you're tired of simulating. And you need to use the simulator of chess, which is fairly cheap, to get the next state, to then input that state to your policy to predict the next action, and so on. Mu0 really, which I haven't described, but the main idea is almost the same as AlphaZero, but just don't use the simulator. Give me the sequence of actions, right? Give me what is the action I take, the action you take, the action I take. This is a sequence of actions like a little language model. And I don't care what the state looks like. I just care about predicting these actions autoregressively like I do in language model. And this actually creates an agent that's as good as AlphaZero, but you don't need the simulator anymore, which is critical, because what the Mu0 paper shows that it can do is it can play games like Atari, where maybe you don't have a simulator or you don't want to run the simulator which is in the game, and so on and so forth. And in a nutshell, then our idea, and sadly I'll skip more details, perhaps we do QA and I'm happy to discuss a bit of the details there, but the main idea that we lift from Mu0 to make it even more general is that in Mu0, right, you still need to plan over opponent's actions, and the environment might be stochastic. If the environment is stochastic, something might happen that is not accounted for in either your action or the opponent action. So what we do is replace the opponent action with this discrete latent representation that we learn. And we think of it as we take our own action. So it's my turn, I think about an action, I take it. And then instead of planning over opponent action, I see opponent and any game really as there's an environment that is taking an action against us, or maybe randomly, right? And so we think of every opponent and everything that happens out of the agent control as part of the environment. And then we model the transition in the environment with a powerful autoencoder, which essentially actually is a bit of like a language model over state transitions, over discrete state transitions, right? Sadly, there's no more time. I prefer to have more questions. So there's a few variants of these, but the TLDR is that this solves many of the problems that I discussed. And maybe to point the results is that with this idea that there's no opponent anymore, that everything is an environment model, we are able to recover and, if you squint, maybe surpass the performance of the best agents that have used the knowledge of that this is a turn-based system, that the opponent action space is the same, and so on, with this model that now is able to be applied, ready to be applied to non-deterministic environments, and crucially plans not over actions, but maybe over state transitions, which is getting us closer to planning over temporal abstractions and so on and so forth. This is an example. You plan over an action first, and after that, you just kind of have this little language model that understands the dynamics of the game of chess. And we also tried this on more visual domains where you see kind of that this world model through these discrete latents is understanding sort of how the world evolves and also representing its multimodality, right? This is a non-deterministic environment. You can see how you roll out this model and it creates very diverse set of samples that will be quite useful for planning. So to finalize, we're adding to this list of models mu0, which crucially over AlphaGo or MCTS does not require the ground truth to model the transitions, right? It models the transitions as part of the modeling process. So you don't require the environment anymore, but it's still only applicable to perhaps deterministic environments. And then the last set of models that we're just starting to scratch the surface on, but this idea of using a BQ vector quantized model of the state and modeling state transitions instead of actions enable all that mu0 enables on top of what AlphaGo couldn't do. But we can apply this to any environment, be it stochastic environment and also partial observable environment. So maybe we're getting actually to a point where we could start trying these ideas on the StarCraft domain, as someone was asking earlier, perhaps. So as a last kind of concluding thoughts and remarks, I think we need scalable model base, but that work across all the domains. And I think we're seeing a very nice and natural transition from some assumptions of knowing the environment to less assumptions, like we train with the better laws. We don't require the environment, and now the environment can be stochastic and partial observable. So I think this trend will continue, and we'll find variants that work better thanks to better inductive biases. I would say, though, I'm not still convinced planning scales as well as learning. So maybe there's a bitter lesson still that planning might not be strictly required as it was thought maybe in 2016 with the success of AlphaGo. But I will say, in fairness, that planning, it would be nice if planning just helps the policy, but planning is supposed to do much more than that. It's supposed to help us to transfer to different versions of the game. So if suddenly we change the rules of Go or the rules of StarCraft, a policy will simply fail. Whereas if we had a good understanding of the dynamics of the system, we might learn much faster, right? So there are ways to see that even if planning doesn't help in raw performance, it might still be a desirable property that we want to induce our models with. And with that, I'm happy to stay for as long as you have questions for, but thank you very much. And also thank you to all the amazing people and teams that provided parts of the slides you've seen today. Thank you so much.
We have time for a few questions. Chris, can go ahead.
Great. I might keep the slides, or I actually removed the slides so I can see people, but I might, let's see. I think there's a way to, yeah, I'll show the it's good to see people's faces. Okay, great. I actually can see people if there's any questions.
So this is Chris Atkinson. My first request is that you make these slides available. The ones you skip through very fast look really interesting.
Yeah. I actually
use them for teaching.
Yeah, of course. I'm happy to make them available. And in fact, I mean, the more like the paper that describes the algorithm a bit better is also coming online fairly soon. But yeah, I'm quite excited about this. I prepared this talk, and I kind of, as usual, I wanted to make sure the first part was clear to everybody, but good point. I'll try to share the slides as soon as I can. Thanks, Chris.
So historically, there used to be a battle between what we'll call the brute force school of thought in chess and the cognitive school of thought. And the cognitive school of thought said we need concepts, abstractions, cognition, and play like a human, or play like we think, our intuition of how a human works. That school got wiped out by the brute force people, but everybody said, Go will need intuition, we'll need cognition, we'll need abstraction. And you wipe those people out a second time. Now you're saying we need abstraction, cognition, yet what you're really doing is data compression. And, you know, is cognition just data compression? And aren't you going to get wiped out by somebody else who has better brute force?
First, I really hope we are going to get wiped out. I mean, our field right now is obviously oversampling over the kinds of things that have worked and keep working for a few years. So I really want to, and in fact, there's some more like out there research directions that I myself am starting to look at as like, you know, I think, for instance, programs are an interesting concept because programs might express things in a way that might make our agents more robust, but you know, how do you search the space of programs? So there's quite a few interesting directions of research that I myself am quite interested to add a bit more structure and more like ideas of variables and, you know, maybe recursion and so on. Maybe they're not exactly the concepts you're referring to, but I certainly hope that a feed-forward, very deep network can do everything as it seems to, you know, some evidence seems to be suggesting, right? So that would be, I mean, that would make, you know, but it would make me happy in the one hand, but also it would make, it would be a bit sad because it just simply, I cannot believe that would, you know, to reach things like, so these systems are very good, right? All these systems are very good, but even the best ones, even the Go, all the examples with you know, with all these, you know, professional beating agents, they have gaps, right? There are issues, there are things that there are mistakes and there are areas that you can exploit, and it's a bit of this effect that you see in computer vision called adversarial examples. But these adversarial examples happen to be sort of a universal property, if you will, of these kind of models, right? Of neural networks that are very deep. So to truly solve these problems, right? To not have to strongly generalize, to be as good as and not fail apart when you maybe play a very weird move. I think we might need this, but at the same time, in practice, yeah, like this is pretty good, right? So I think when we start doing things like even machine translation and so on, these happen to be, you know, according to all the metrics right now, the best models that don't require any linguistics knowledge and so on, right? Which, I mean, I think it's kind of the story of maybe the deep learning wave that we're living, but I certainly hope, and I think many people hope, that someone out there is going to come up with something new that's going to revolutionize machine learning, but we'll see. There's hope. I'm working, you know, I'm a bit conflicted working on both sides as much as I can, but yeah. Thanks, Chris. Any further thoughts? I see you're muted.
So this is Carnegie Mellon, and we have a long history of studying decision-making in organizations. Mm-hmm. And if you put the constraint on your compute power that it comes in chunks, and the mm-hmm. chunks can only communicate with low bandwidth, they can't exchange a whole deep network, perhaps that forces that computer system to think in a very different way. Yeah,
that's a very nice thought. In fact, when especially with the chess results, because Go was I mean, the bots in Go were so bad that, yeah, like AlphaGo was just, it was useless to compare it to kind of state of the art, let's say, similar to StarCraft, I must say. The state of the art was very far behind. But in chess, obviously there are systems like Stockfish, and that community, and as part of the release process and the paper and so on, you know, the idea of how many watts are these models using was discussed a lot, right? Because even though Stockfish is a program that is inherently sequential and maybe that cannot run as fast as these very parallel like neural networks that are kind of ruling by using more power and better hardware, but maybe doing more brute force, if you will. I think that trade-off was discussed a lot. So you might find those discussions from even the paper and forums interesting. But I agree, like compressing information is one thing, but compressing, maybe capacity or amount of power use, maybe another direction that some people start doing. There's a very interesting paper from Alex Graves and co that is called adaptive computation time, and it's a neural network, but it's deciding how many layers it uses depending on its inputs, and then it never really quite worked. But the way to make it work is to add a cost for compute. But that for us deep learners, that is like, oh, I'm giving up accuracy for something that I don't really maybe care that much about, right? But I think there are quite a few interesting directions on compressing and more inductive biases to make the system maybe more efficient and use less floating operating instructions and so on. That's quite an interesting thought. And again, many of us, especially because training these models is expensive, start to also think about sparsity and other things that might actually end up helping in the long run, even though we might be using them for more practical reasons right now. Cool, very good questions. Yeah, I like this. Any more kind of questions or thoughts about anything? I'll definitely share the slides with I guess Ayush, and you can share them with the group, or I don't know, like in the list, right? But any questions about?
I'll let somebody else ask a question.
Alex?
Yeah, let's see. Any other questions from anyone?
There are Alex.
Alex,
yeah. Great talk.
Thanks.
I was just wondering, so you talked, you skimmed through the VQ hybrid, and it's really new to me. So I'm just trying to think of a way to wrap my head around it. Are there any limitations to that? I know you talked about it being like slightly better than not like non-compressing it, considering the opponent. Are there any restrictions to that?
Yeah. I mean, the intuition there is kind of a bit of a build up, right? So sadly, like that part, I couldn't describe too well, but let me do it now. Okay, so the build up is we have a very good kind of learning search hybrid system, if you will, which is MCTS plus a policy network and a value network. So part of why that works so wonderfully, even in mu0, is because the actions are discrete, right? So you can always discretize actions, but especially in Go and chess, actions are already discrete. And so you can search over actions that you and your opponent take in using the MCTS that is designed for discrete, although there is continuous MCTS as well that actually could be used. But we wanted to change minimum amount of components, right? So we wanted to search over discrete spaces, okay? Now, the state space for chess, it's kind of discrete, but it's a bit annoying because there's all the pieces, and you could kind of map it to a single integer, and that's very uncompressed version, right? There's all the pieces, and yeah, you would have a very large integer, and you could try to search over that perhaps. But these models that are essentially trying to do that step of, given the state and given the action that you're about to take, predict what's the state going to be like when after I play, right? So you're trying to essentially use the opponent as part of a stochastic environment, right? You're playing chess and your opponent is part of the environment. So that input to output mapping can be learned via autoencoders or variational autoencoders. But because we wanted to have a discrete bottleneck, right? That we want to have a version where we have a sequence of discrete variables. What we do is just simply train the model with vector quantization, which is the simplest thing you could imagine, right? You have a continuous vector in an autoencoder as the bottleneck. And then we say there's a dictionary of size, let's say 2000, given this example, maybe it's about 2000. And then you take the continuous vector, the number 1906 in this case, right? That continuous vector, you pass it through the decoder and you would obtain this chessboard decoded from the move you just did. But of course, you don't need to do that. You just can keep searching over 1906. That's the action. And you have a multinomial over these 2000 variables. And then in the next time step, your model, instead of searching over a multinomial over action, searches about a multinomial over what's the next discrete state I'm gonna see. And the limitations of these, though, the main one, let's say, is that you're doing this in a two-stage process. So you say, okay, like first you have a game, here is the game of chess. There's all the games in the world. Compress the states so that you're finding reasonable integers to map to and from, given the action and the past state, okay? And you're trying this, and no one tells you like how many bits do you really need, and also are you maybe ignoring certain things that you shouldn't ignore. Maybe you think that, you know, in this transition maybe this pound is irrelevant, so you don't encode it, but maybe later in this rollout it turns out that there's going to be a critical move that would involve this pound, and now it's not in your kind of imagination, and now you're done, right? So it still kind of has this reconstruction first, and what to reconstruct might matter a lot in terms of what matters to reconstruct to plan better for the game. And that's probably the main limitation, that it's still trying to reconstruct faithfully everything in the board, statistically speaking. And if you reconstruct too little, it might suffer from the model not being accurate, you know, further as you go deeper into the search tree. And if you reconstruct too much, then you haven't solved any issue because you have a huge branching factor. You never revisit nodes, so you're basically resorting to essentially like brute force, which is not great.
Right, that makes sense. Thank you.
Cool. Yeah, but so I think, I mean, this is not, I don't think this is the solution. This is just kind of, okay, this is a problem. People are thinking about this. This is one example of a possible solution. I think there's already a few others that obviously like we're gonna like discuss in the paper in more detail, but I think it gets to the bottom of, yeah, the environments are not always fully observable and deterministic, obviously, as we know, right? So cool. Any other questions about maybe the last part or really any other part or anything? I mean, I'm happy to discuss anything.
Tanmay?
Yeah. So I guess a high level question, so throughout your talk, there was this common theme where the initial research that's sort of say enabled success in say chess or Go or I guess StarCraft as well was based off of imitation learning or based off of this human gameplay data. And it's also true that like you then do RL, but I think like as you move on to more complex games like StarCraft, where say the simulator is expensive, or when you move into say things like robotic tasks, for example, do you expect that you're going to have to let go of pure RL or at least rely on imitation more, or do you think that you can still sort of push on with I
really like this question. I mean, I guess the talk wasn't meant to be about like imitation versus reinforcement learning, but this is maybe one other, like it's a different talk that you could give because there is a tension perhaps about this, right? And in fact, when discussing with colleagues, right? You look at AlphaGo uses imitation, then AlphaZero removes imitation. So like now we kind of go to StarCraft, and we tried without imitation, and we were stuck in these deep local optimas of like games that were not, you know, they just look like workers attacking workers, and I mean it was fun to see, but it really wasn't playing the game at the full meaning of playing the game. So this tension is everywhere. I think it's like, okay, we have these discussions, do we need imitation or not? My belief is that if pure self-play from scratch has worked, you know, you basically, I think it's just kind of a probability game, right? Like the probability of having a move that sort of is better than the previous move is maybe 10 to the minus 6 or 10 to the minus 5 in a way that, okay, you actually are going to sample that move and you're going to then improve your policy largely. But in many domains, and StarCraft is certainly one of them, the probability of creating, you know, this building in this location and then creating workers that will go mine, so they give you an income, and then you figuring out that income is actually usable to create more, you know, more units and win the game. This is very low probability event. If you don't want to have any sort of prior knowledge about, maybe it's not this prior knowledge, you could argue, well, it's not about the game, this is more like economic knowledge. Then, you know, that's an interesting question, right? Like where do the priors and the imitation comes from when we learn more and more about like complex world sort of world dynamics, and when is it like, oh, just give me the environment, give me the laws, and I'll just do it from scratch. And I feel like imitation is here to stay. I almost have like the challenge that anyone that wants to do AlphaStar 0, I mean, I will be quite impressed, because I think quite a few fundamental issues with that in terms of zero probability events. But of course, you could, probably the same argument was valid for Go, before it happened, right? So I might be wrong, but the orders of magnitude are now in a scale that I think, well, maybe unless we had like an insane amount of compute, that's not going to happen anytime soon. But again, I might be wrong, and it would be fun to be wrong, actually. So maybe you can come intern with us and prove me wrong. I'm looking forward to that.
A quick follow-up on that. So you talk about this low probability events and how it's just hard to chance upon them with RL. And going back to something you mentioned in your talk about planning over temporal abstractions. Now, do you think that like once you start building some abstractions, either through RL or imitation, whichever, you are sort of increasing your chances of hitting upon those actions just because you're like looking at the relevant abstraction sequence, maybe?
Yeah. So I mean, I think, and as I said, there's almost like, I guess in research there are all these fields that they are they need to be researched, but at the current time, maybe as Chris said, is like, okay, like maybe all you need is like a big deep neural network. But of course, hierarchical RL also was something that we initially in the project thought, of course, we'll need hierarchical RL to play the game of StarCraft. In fact, when I worked on this at Berkeley with Dan Klein and the Overmind team, we thought, yeah, this is a great domain because, of course, you want to, okay, I want to get a lot of money to build this unit, and then you kind of plan, you have these options, right? Like these higher level goals, and then you achieve them through low level execution. So it is possible that if we advance more on hierarchical reinforcement learning, then the problem of vanishingly small probabilities may be relieved, right? Because maybe there are some initial skills that you will discover, like, oh yeah, managing your economy and then expanding might be easier to be discovered. By easier, I mean non-zero probability, basically. So it's true. I see options on why my statement is not like, it's these techniques are supposed to fix precisely this issue of exploration, exploitation, of course, and all these that we've seen so clearly when we applied self-play and even hierarchical RL in the game of StarCraft. But at the end of the day, you need some amount of maybe domain knowledge, which is when you start being a bit like nervous about like, oh, should we add a pseudo reward, right? That rewards the agent for mining more money. And then, of course, doing that is nice. It's kind of, you program an agent through kind of maybe telling it what you think is important to solve this domain, but it starts to deviate a bit from the pure sort of learning paradigm that we know eventually scales quite well, and otherwise you might create some suboptimal policies through your kind of injections of knowledge. However, those sometimes are quite good and they are efficient to get you off the ground, right? So I think if it's imitation, like as in like here are the actions that people do in this game, or maybe it's another kind of imitation which is a bit higher level, some form of imitation I think will be like needed as we go from narrow domains that have n actions and okay, like trajectories are finite and so on, to these more open-ended sort of domains that might not even have a reward well defined to begin with.
Yep, awesome.
Great
Thanks.
question. So thanks, Tanmay.
Okay, we have 3 more questions.
Okay, yeah, let's do this. Let's do this. It's the end of the day for me. So I need to check the news though, but well, these days, yeah.
Chaitanya, you can unmute yourself.
My question is based on the VQ state of the last section of the talk. So because you're compressing states, is it possible that you might end up having a state which is not possible at all? For example, the white pawn and the first rank might not be a possible state, or is it something you
absolutely
correct later on based on your information about the model?
Yeah, this can happen, and in fact, it's the reason. I mean, that this happens. It would be perhaps the reason to. So this is actually a good and a bad thing. Okay, if you want to compress, which every model, like both BQBAE and also language models and these policies, they all try to compress. If you perfectly compress, you're not going to generalize. Okay, like this is the I mean, yet another topic in machine learning which I love, which is, you know, where overfitting versus generalization. Okay, so if you fully understand every transition that you've seen in your data set of transitions that you created through self-play or through looking at other people play, then your model will always be correct, will never generate something that isn't there. But as soon as your opponent does a move that is not in your data set, then your model absolutely loses all the guarantees, and you'll start basically having a completely nonsensical model because you've never seen this particular position. And in any of these games, almost every position you're seeing is new, right? I mean, in chess, you know, there's quite a lot of positions. In Go, even more, and in StarCraft, well, I mean, there's even more, right? So I think precisely why this is not happening, that you might sometimes make an error, is actually the reason why you actually get to generalize, and why, you know, when people, I mean, hopefully all of you, like, it's an impressive demonstration of language modeling, but if you see all the GPT-3 demonstrations, you know, GPT-3 compresses a large data set of text, and now you can query it, or like you can kind of prime it with some words that it's probably never seen exactly like that, and it produces sensible continuations, right? So, but of course, mathematically or like there's no guarantees, right? So indeed, the model might go off the rails, but in general, these models, the more data you train them with, and with reasonable inductive biases into the architectures and other things that are important, this doesn't happen enough to be identified as a problem. But we totally have seen in chess even, which is a fairly narrow domain, very discrete, you know, very nicely constrained. We've seen the model sometimes, of course, will predict a sequence of a transition that doesn't exist, right? And you kind of have one of these paths that goes down the tree, that a piece disappears or something happens, and you know, clearly you know that dangerous territory to be like playing those moves based on that information, right? But it would be bad if you always were correct, because then you wouldn't have a smooth distribution over the things you will certainly have not seen. So it's a trade-off. It's a tricky question, but yeah, I like it. Okay, good. You guys are very smart. Okay.
All.
Hello. Thank you, first of all, for the interesting talks.
Thanks.
There was some interesting ideas about abstraction, discretization of state transitions, but state is still somehow implicitly represented in the network. So do you have any ideas of how to explicitly store and retrieve the state? So more than differential neural computing, which has been introduced some years ago. Are there any updates on progress in that direction?
The state of, I mean, yeah, I'm not sure I follow. Like the state in, you mean in the last part of the discretization?
So for example, of keeping track of units. So how do you keep explicitly track of entities? So can you somehow store what's happening, or update it somehow, so having explicit memory rather than it being implicit?
Yeah, so in the, right, so depending on the domain, the observation already will give you some means to store, like, what, you know, what it's in a way it's a form of memory, right? So maybe to be concrete, in StarCraft, even though it's very important to, let's say, keep track of all the units you have, okay? And that can happen, hopefully your LSTM is tracking that you're building these units and you have them at home and you could use them to defend. But at the same time, the game state actually, in that case, for this particular instance, explicitly exposes the units, because it has a way to access the units through, you know, control groups and things like this. So sometimes the memory of your system is either implicit, and it's very hard to then know what the system knows or not in your, you know, neural net vectors. But sometimes it's also explicitly built into your observation, which then is there, and then it's much easier to use it. But maybe the best paper to look at a very wonderful analysis of what do these neural nets really know about the state of the game. The Capture the Flag paper from it's also from DeepMind, but they do a very nice job where they first train the agents to play this Capture the Flag game, which is a collaborative game where you go and you capture the flag, you bring it to your base, and so on. And they did a lot of analysis after training the agents to what could they extract from, they probe the state of the neural network by adding, let's say, a linear probe that say, hey, from the state, could I predict if I know which of my colleagues have the flag and whether the flag is close to home or not. So they have a way to visualize almost what you know as the player, as your internal state of the representation. And in fact, that paper is almost all about understanding what we know about the world from the agent's first person view. And so I would recommend take a look at that. There's lots of cool analysis and visualizations on the capture the flag paper from like maybe 3 years ago or so. But there's some techniques that you could use, like kind of a posteriori to extract this information from the neural network vectors. And it's imperfect, and indeed explicability of these networks is not always the best. I mean, someone was asking earlier, why did AlphaStar do this building here? I mean, yeah, we don't know, right? Like it's hard. I mean, it just samples an action and it happens to want to build it there, right? But yeah, it's very hard to know this. Cool. There's a last question, maybe, Ayush, you said?
Yeah.
Okay.
Hello.
Hi.
Hey, great talk, first of all. And I'm like a big fan in terms of how the progression has been from AlphaGo, like to Go, chess, and then to AlphaStar. I think one of the main things which is like highly intriguing to me is like the action space and how much it has increased from Go to all the way to AlphaStar. And my question is actually in a similar direction, that right now we have the policy networks which are like sort of discrete at the end. Like the architecture is fixed in the sense that if there are n number of total actions, the output have to be in those n outputs. And like a particular unit at the output would refer to a specific action. But is there any thought, or is there any new direction in research for going in like a dynamic policy network? Because like there are often like situations where states evolve and the action spaces change depending on the states. So is there like any direction that?
So let me just put this particular architecture, because this is already happening here, even though at the end of the day in practice, we operate with fixed vectors. But this architecture is one of the main challenges in complex games and in complex. This is essentially like how you see any modern agent to operate with, let's say, any program, is that there is an API. The API is defined, and then as part of the API, you need to issue actions that conform to the protocol that the API requires, right? So in the game of StarCraft, we literally use Blizzard's network. By network, I mean the network that transmits data from me to you when I play against you. And we use that protocol buffer, like that, the same protocol that encodes when I do an action, your client, you need to know what action you made. So we use, okay, that's the action. That was as simple as that. That's what we decided, okay? But of course, that action is not like, oh yeah, one of the 4 buttons, which one it is, right? It's very complicated. But I think this is already happening, because what you do is you have a conditional action, right? So depending on the state, right, what actions are even available to you are, again, depending on the state, right? So one thing that you do, and you can do this easily because thanks to the chain rule of probabilities, is to say, okay, so there is actions that are possible only if some previous sub actions that are only possible if this previous sub action is sampled. So you literally do this, right? So for instance, the first thing we output is the action type, right? And in StarCraft, there's an action type that is, let's say, move the camera, okay? Move the camera only requires an argument, right? It's the API, right? So it only requires one argument, which is, where do you move the camera, right? The camera can be moved anywhere on the map. So it doesn't require like any of these other arguments. It only requires a target point, right? So when you train this network, all these outputs are masked out. They are ignored, right? The loss is not backpropagated through here. And then when you execute this action, it's like, okay, I'm going to create an action protocol that is move camera that requires XY coordinates. I'm looking at this, and then I'm sampling, and those are where I'm moving the camera. There's an action that's no op, that no op requires no argument, and then you sample no op, that's it, right? And then there's some actions that maybe require to select a subset of your units. Now, what we did for that is the assumption that at most you pick 64 units at once of your own. That's a limitation that AlphaStar has, that maybe if professional gamers knew it, okay, they could play with this, but that seemed reasonably good statistically speaking. We looked how many units usually are picked in actions, and it was barely more than 64. So the way that works is there's a recurrent mechanism that looks at the set of units. So let's say you have 300 units, and then one at a time, it picks which unit it wants next to be selected, okay? So it picks the first one, the second one, the third one. And at some point, you're done picking. Then you have a special unit, a unit of a special type, which is, I'm done picking. I only want these 3 units to issue this command. So then your network points to that last unit, that special unit. Then this unit, in practice, what you do is you repeat that output forever. It's end of sentence, right? So you say, I'm done picking units, end of sentence, and that's what creates the action. So it's already very context dependent, the actions and how you sample them. And you could go even one step further and generate literally the protocol buffer that is a set of bytes that it needs to be sent to the engine, which would be literally generating 1 byte after the other. And this would work as well. I mean, it maybe not work as well, but it would definitely work. And all the language models have the capacity already to say, I'm outputting words, and when I'm done outputting, I'm going to say, I'm done outputting, right? So very similar to how it's been done in language model for a while. These mechanisms in policies where action spaces are maybe more like conditional on the state deal with these very naturally. But when you train, you mask the losses, right? So you mask the actions that are useless because these arguments are not used for this particular action type, say. And then at inference time, you just run sort of the policy, and then you sample an action, and then you know what, given this action, what arguments to expect, and that's how the program does the playing. And funnily enough, even though the game obviously will never allow some actions, when we trained, we actually don't use this information. So if there's an action that is forbidden, let's say because you don't have enough money to build this building, we tried both options. I mean, you could impose this constraint at the top. We say, okay, like, look, this action is not available, so don't try to issue it. But because of imitation learning is so powerful, we could ignore these constraints. We just let the network output any action, and the network understood the game enough that it would not almost all the times output actions that were quote unquote valid. Some were invalid, but most were valid. Otherwise, it would not play very well. But yeah, I think that challenge is being addressed by basically autoregressive models, the chain rule, and it's fairly well understood, and it's very powerful. This always works. I mean, I don't know. That's all I can say. Every time I try this autoregressive outputting of complex data structures, it really, like LSTMs or transformers or the like, are very, very powerful.
All right, thank you.
Cool.
Thank you for the answer.
Well, there's one last question. Do you want
Okay,
to take?
let's do the last one. Yeah, let it be the last one.
Ricardo?
Yeah, so I put it in the chat, but maybe I just can repeat it. So first, thanks for a great talk. So
thank you.
Relating to AlphaStar, so for you, what would be the main contribution to highlight that has been important for the general RL or robotics community? So for example, what algorithmic improvement or technique do you think that has contributed to, has had a major contribution?
It's a very good question. Many times, so there's, when you work on a project like big or small or long or short, there's 2 kinds of contribution. First, it shapes you as a researcher, okay? So a lot of what I do now is because of what I learned in projects, even though there might be projects that they don't even get kind of impact outside of, I mean, you write a paper and, sometimes it is more impactful than other times. So the first kind of contribution that's quite important for researchers is how it impacts your own research agenda, right? So maybe on that note, I think AlphaStar, first, for me, it was a way to learn reinforcement learning, right? So I learned the limitations, I learned what works, what's not, what are the challenges and what not. And from the project itself, one thing that's very clear to me is that imitation learning is very important, right? Initially, I thought, well, imitation learning is the thing that is kind of you don't want to do, you just want to do RL and be as pure as possible. I think that view for me changed for my own sort of future projects and whatnot. I think imitation learning is powerful. There's problems. The main one is sometimes you cannot get access to data to imitate from, but I think it's something to be kind of explored in itself, even as the main object of interest. So maybe that's, if I have to pick one, that's the biggest lesson. Things that I brought from my own past influence from my projects to this project was precisely this architecture. So how to deal with this complicated action space, for me, it was very clear given some work that I had done on building parse trees for language, and of course the sequence-to-sequence modeling, and even distillation as part of how to do imitation plus reinforcement learning. Now, techniques that I think are very powerful for the community to just leverage from the project. So I'll maybe one per area that I didn't describe, of course, the whole project, but from the architecture, I think that if you have a complicated action space, you just do the proper join probability with the chain rule and it's gonna work, right? So basically that's to me, like, I think everyone should feel bold that even if they have a complicated action space to interact with a complicated program, they can just use similar techniques to point to subsets, to create actions with sub actions. All these things, I think, very convincingly can work at scale, especially if you have imitation learning data. So from the architecture side, I think that's maybe the main technique. Although particularly I like this recurrent pointer network mechanism to pick subsets out of sets. I think that's powerful. It's been happening in graph neural networks research, so it's not that it wasn't fully a surprise, but that's good. Then from bridging both worlds of imitation learning and reinforcement learning, one thing that we did in this project that always works is distillation from imitation policy to reinforcement learning. Okay, so distillation is a very simple technique of, okay, I just take the logits and try to approximate them with your network. So the idea that you must be close in functional space to your original imitation learning policy as you train with RL was very important. And I think that's just a technique that very simply put, if you start from imitation, you need to use it if you want to keep the diversity around. That was by far the most effective and very simple, actually, idea that works very well. And I think there's some works maybe that relate to that, but this was astounding evidence that this works. And maybe the last one, that it's more like future research. We have this system of agents playing each other that I haven't described at all, which we call AlphaStar League. And so I think there's a very interesting multi-agent aspect that is very powerful, that it's not unique to StarCraft, but I think we saw it quite clearly, which is the idea that if you do self-play, you play against yourself and things drift and there's some issues with self-play, right? In StarCraft, what we did is you have many agents playing each other, but the goal of all the agents is to create a single agent that's going to be as strong as possible. And I think that is what the AlphaStar League tries to promote through heuristics. Is not an elegant solution. I think it's, that it works, but it's not like, oh, that's mathematically beautiful. But this idea that you have many agents to help you be robust against many strategies is very powerful. And it's very similar actually to adversarial training in neural networks, right? But that would be maybe one that I can see lots of follow-up work, but as evidence that, okay, this really worked at scale and these agents became much more resilient to adversarial strategies. I think that was maybe from the last part of the project what I would also say, yeah, that's the biggest contribution in the multi-agent area, right? So architectures, then imitation, then RL with distillation, and in multi-agent, this idea of a league for improving one single agent. Those are all very powerful ideas that we were exploring in the project that I think, yeah, like I would like to see more progress, but I think we advanced the understanding at the very least of this. How about, I'm curious, what do you think? I mean, if you know the project, what do you think is the most surprising? I mean, maybe it's a very complete different thing. So what do you think?
I like it the way you put it. So I thought yeah, I think that the answer was very good.
Okay, okay. But if there's one that I missed, email me. I mean, I would love to hear.
I like the idea about creating an agent that have a bunch of agents that help one agent to
yeah, that's very powerful. Yeah.
I like
okay. Yeah, I like that you like that. I mean, there's very cool work on like more rock, paper, scissors, like very simple environments, trying to understand these dynamics for multi-agent and non-transitive games. But yeah, this is a demonstration of this idea at scale that I think worked quite well, and it's still very early days as well at the same time.
Thanks.
Cool. Thanks.
Great talk.
Okay. Thanks, Oriol.
All right. Yeah, thanks everyone.
For a lot of time. Yeah,
I'll share the slides.
Yes.
Yeah, thanks a lot.
Thank you. Thank you.
All right. All right, there's a chat. I'm gonna read the chat, but feel free to leave. I guess I guess you're asking these. Okay, cool. Yeah, thanks a lot for being at your place, hopefully safe. And yeah, see you soon. I really want to visit Pittsburgh. I think last week there was yet another reason to visit Pennsylvania. So I'll come as soon as traveling is allowed.
Yeah.
Cool. All right. See you, everyone.
Bye.
Bye.